uniform random variables. This one is a bit easier. Uniform random variables. Oops. We say that X is a uniform random variable on an interval. On the interval, say alpha, beta. If its PDF is the following. If its PDF is given by the following. F of X is equal to 1 over beta minus alpha if X is in between alpha and beta. 0 otherwise. Since B is bigger than A, alpha is less than something that's less than beta, alpha is smaller than beta, beta is bigger, bigger minus smaller is positive. Beta minus alpha is positive, and 1 is positive. You divide two positive quantities, you get positive. So either f of x is this positive number, or f of x is 0. F of x is one constant or another. But most of all, none of them are negative, so it's non-negative. Now, what would the cumulative function be? What would f of a be? Remember, this is the integral from negative infinity to a of f of x dx. What will this equal? Well, let's draw this f of x function. I'll assume alpha and beta are positive. Well, if x is not between here, we get 0. Okay? From negative infinity to alpha is 0. And then bigger than beta is also 0. What if you're between alpha and beta? What if x between alpha and beta? Well, it says, if x is between alpha and beta, you get this quantity. 1 over beta minus alpha. There is your function. Just like the rest of it, let me put it in red. It's actually open here, and closed here, and closed here. Okay. Well, you're going to get 0 if x is less than, let me write that, if x is less than alpha. Okay, now, if x is bigger than alpha, remember, x is less than alpha. I meant to say if x is bigger than beta. So I add up all the area up to, say, that value. Well, here it's 0, but then we get this area, and then we get nothing again. Well, this area, the base is beta minus alpha times the height. The height is constant. It's always 1 over beta minus alpha, which is 1. I should have written alpha here. So sorry. Beta minus alpha. You get 1 if you're there. Now, what if x is in between alpha and beta? And I've been making a silly error. Nothing major. I should be saying the letter A, not X. We're adding up all the area up to A. Now, what if A is between alpha and beta? Let me clean this up a little bit. What if A is right there? That is, what is that area? Well, simple. So it's a rectangle. It's the base, which is A minus alpha, times the height. The height is always 1 over beta minus alpha. Times the numerator, you get A minus alpha over beta minus alpha. I'm hoping I have enough room to write this. Actually, let me move this over. Look, let me write this bigger. I'll write what we just did first. The total area is A minus alpha over beta minus alpha, and that's if A is between alpha and beta. You get 0 if A is less than alpha. You get everything if A is bigger than alpha. That is exactly what the cumulative function is. Everything up to x equal A. Everything up to the x value A. Okay. Let's draw both functions. So uniform random variable, the height is constant. And it's always 1 over the difference, 1 over the length of the base. That's the only way the PDF will add up to 1. Alright. The f function from alpha to beta, here's 1 over beta minus alpha. It looks like this between alpha and beta. Otherwise, it's 0. It doesn't say it can equal alpha or beta, hence the open circles. And otherwise includes alpha and beta. That's f of x. This whole thing is f of x. Now, what about f of a? What about f of a? You have alpha, you have beta, you have 1 over beta minus alpha. Well, if A is less than alpha, is 0. If A is bigger than alpha, this really shouldn't be what I wrote. It should be 1. If A is bigger than alpha, you're going to get 1. And between alpha and beta, it just goes up to 1. So here is the f of a formula. That's the CDF, the cumulative distribution function. Once you hit B, you already, all the probabilities added up to 1. Can't go any higher. Okay. Let's find the expected value and the variance of a uniform random variable. So E of x, by definition, is the integral from negative infinity to infinity of x times f of x dx. For most times, we have 0. Only between alpha and beta are we not 0. X stays x, but f of x is simply 1 over beta minus alpha dx. That's a constant. I can pull it in front. 1 over beta minus alpha. The integral of x dx, those are the limits. The integral of x dx, that's simple. That's x squared over 2. The power is understood to be 1. Add 1 to the power when you integrate. Divide by that new power. And this is from alpha to beta. I'll multiply those two. I'll factor that out. You have 1 over 2 times beta minus alpha times this. You plug in beta, you get beta squared. Minus, you plug in alpha, you get alpha squared. A little algebra, and we'll be done. Beta squared minus alpha squared is beta plus alpha times beta minus alpha. The beta minus alpha cancels, and you get 1 times beta plus alpha, which I hope is obvious, over 2. And that is your expected value. Notice it's the midpoint of alpha and beta. What's the midpoint of those two numbers? Oh, add them up, divide by 2. It's the midpoint of alpha and beta. So that is the expected value. Let me write this up here so I don't forget. The expected value is alpha plus beta, or beta plus alpha, over 2. Now we want to find the expected value. We want to find the variance. And usually when you have the expected value, which we have in front of us, the way you find the variance is just to calculate e of x squared. Just calculate e of x squared. And again, the motivation for that is one formula, or one way of writing the formula for the variance of x is simply e of x squared, something we don't have yet, minus e of x, which we do have, but we have to square it. I know how to square something. I need to find e of x squared. E of anything is equal to the integral for a uniform distribution function, or uniform random variable. E of anything is the integral from negative infinity to infinity of the anything times f of x dx. But f of x really only goes between alpha and beta. Outside of that, it's 0. X squared times, and f of x is a constant. It's always 1 over beta minus alpha dx. This constant I pull out in front. Integral of x squared dx is x cubed over 3. So I get 1 over beta minus alpha times x cubed over 3 from alpha to beta. This here is a constant. It's 1 over 3 times beta minus alpha. Plug in beta. You get beta cubed minus, plug in alpha. you get alpha cubed. Now, I'm not going to review algebra, but that's the difference of squares, and you should know how to factor the difference, the difference of cubes. First, you write beta minus alpha. That's one factor. The other factor is you square the first one, plus you multiply the two, beta alpha, plus you square the second. And it turns out that that factor cancels. So erase this on the bottom. That factor cancels. So you get 1 times what's in the brackets there, which is beta squared plus beta alpha plus alpha squared, all divided by, 3. Okay, that's e of x squared. Let me write that down up here. E of x squared is nothing more than beta squared plus beta alpha plus alpha squared all over 3. With this information in algebra, we can find the variance. So let's get rid of all of this. This is definitely a problem you should be able to handle. If you know how to factor cubics, or the difference of cubes. Okay. So, the variance of x is e of x squared, beta squared plus beta alpha plus alpha squared over 3, minus e of x squared, alpha plus beta over 2, quantity squared. Okay, so keeping the first fraction the same way it is, I will now square the second. You get alpha squared plus 2 alpha beta plus beta squared all over 2 squared of 4. The common denominator is 12. I'm going to multiply this by 4 over 4. You want to change the way something looks, you multiply by 1. And multiply here by 3 over 3. Because 4 times 3 is 12. So now, subtracting, and the denominators are 12. You get 4 beta squares plus 4 beta alpha plus 4 alpha squared. 4 alpha squared. Minus 4 times 3 is the same 12. You get 3 alpha squared, 3 alpha squared, plus 6 alpha beta, plus 3 beta squared. Okay. The denominator won't change. You have 4 beta squares, and you are taking away 3 beta squares. That leaves 1. 1 beta squared. You remember, beta alpha is the same as alpha beta. You have positive 4 alpha beta, and you are taking away 6 alpha beta. 4 minus 6 is negative 2 alpha betas. You have 4 alpha squares, and you are taking away 3 of them. You have 1 left. It turns out that that numerator is nothing more than beta minus alpha squared over 12. And that is the variance of a uniform random variable. I know it is. We derived it. Both the variance and the expected value. Now, I said earlier at the beginning that these problems are easier. And let's do a couple. Let's see if I'm right or not. Suppose x is uniformly distributed over the interval 0, 10. If x is uniformly distributed over the interval 0, 10. Find some probabilities. Find P of x is less than 3. The probability that x is bigger than 6. The probability that x is between 3 and 8. Basically, we're finding areas of rectangles. If I were to draw this between 0 and 10, that's 10. So the height must be the reciprocal. We are in this rectangle. And the reason I know the height is 1 over 10, this rectangular area must add up to 1, must come out to be 1. So we want to know the chances that we're less than 3. Okay, 3. How much is this? Well, the base is 3, and the height is 1 over 10. 3 over 10. Bigger than 6. What are the chances I am in here? Well, the base is 4, and the height is 1 over 10. It's 4 times 1 over 10, which is 4 over 10, which you really should reduce. 3 to 8. Since I drew on this picture so much, let's draw it again. 1 over 10 goes out to 10. So we want to know the chances of being between 3 and 8. That is, what are the chances we're in here? Oh, the base is 5, and the height is 1 over 10. Base times height. 5 over 10, or 1/2. Just finding areas of rectangles. You know the base, well, we know the height is always the same for a given problem, and this problem is 1/10, and we find the base. We know it goes from A to B. The base is B minus A. In the last problem, it went from 3 to 8. You want to know how long this is? Just do 8 minus 3, and you'll get the base, which is 5. The height is 1 over 10. One last comment for the height. This is alpha, and this is beta. So the height is 1 over beta minus alpha. 10 minus 0 is 10. That's the height. 1 over 10. Even if you use the formula, you get the height. Now we are waiting for a bus. Okay, we're waiting for a bus. A bus arrives at a specific stop at 20-minute intervals, starting at 6 a.m. What does this mean? The first bus comes at 6 o'clock. The next bus comes 20 minutes later. The next bus comes exactly 20 minutes later. And then 20 minutes later. And then 20 minutes later. And that's the way it is. Passenger. If a passenger arrives at the stop at the bus stop at a time uniformly distributed. That's the key word or key phrase. Uniformly distributed between 6 a.m. and 6:20 a.m. Okay? What is the probability that the passenger waits less than 5 minutes? What is the probability that the passenger waits greater than 10 minutes? Okay? So it's uniformly distributed. 20-minute interval. 6 o'clock to 6:20. 20-minute interval. B minus 0, or B minus A, is 20. The height is 1 over 20. Here it is. So we want to, and this is how long you wait. You wait 0 minutes, or 1 minute, or 7 minutes, or 18 minutes, or 19 minutes. This is how long you wait. Okay? You wait less than 5 minutes. 0 to 5. Let's make that 0 nicer. What is the chances you are in here? Well, it's a piece of cake. The base is 5. The height is 1 over 20. If you multiply that out, you get a quarter. You get a quarter. 5 over 20 is a quarter. The probability you wait more than 10 minutes. Well, 10 minutes is right in the middle of 0 and 20. Half the times you wait less than 10 minutes, half the time you wait more than 10 minutes. I bet the answer is going to be a half. More than 10. Up to 20. You're not going to wait more than 20 minutes. The bus comes every 20 minutes. How can you wait 23 minutes? The bus should have come. Okay, so you only wait up to 20. The base is 10 times the height. The height of this rectangle is 1 over 20. 10 times 1 is 10 over 20. And like I suggested, you're going to get a half. Half the time you wait less than 10 minutes, the other half you wait more than 10 minutes. The chances that you wait exactly 10 minutes, well, that's not going to happen. You know, there's a lot of numbers around 10 minutes, like 10.00003 minutes and 9.99998 minutes. Okay, this actually completes their section on uniform random variables.